Problem 18.27. Okay, this question starts off with quite a bit of background information talking about managed funds and their ability to provide a highly diversified portfolio that an investor may not otherwise be able to achieve. The main thing to note is that we have different strategies for our funds. There are capital growth funds, current income funds, equity funds, and so forth. Now we've got a table with some information of the level of return over 5 years for a sample of investors for various categories of managed funds. The key here is when we have a look at Part A specifically, it says determine at the 5% level of significance if there is evidence of a significant relationship between the level of return and the type of managed fund. There are different strategies and we're wanting to see whether there's a relationship between what kind of returns you get and the type of managed fund, so the type of strategy that they're using. We've got 5 different strategies listed, and then in relation to level of return we've classified that as either high, medium or low. Now we're wanting to see if there's a relationship between these two variables at a 5% level of significance. So we know that it's a hypothesis test. We've got our alpha. The trick is the fact that we're looking to see if there's a relationship. Now that tells us that this is a chi-squared test for independence. Remember, that's the test we can use when we have two variables with at least 2 levels each. Here we've got one with 5 levels, one with 3 levels, and we're going to see whether the two variables are independent or whether they're dependent. So that's how we can test to see if there's a relationship. Okay, so I've got the observed data, but not the row and column totals. So my first step, knowing that I can use the row and column totals to come up with my expected results, I would always add those to my observed data contingency table. So you can see I've gone through, we've got all of the row total, so 118, 95, 127, 116, 53, and then we've got our column totals for high, medium and low, so 143, 167 and 199, giving us a grand total of 509 funds. It's always a good idea if you're actually doing the totals yourself just to double check that all the rows add up to 509 as well as all the columns. It's a nice sort of double check to apply. Now from there, yes, it's a fairly large example, this one that we've got, but we can go through fairly systematically and work out the expected results. And remember, the logic of this test of independence is to compare what we've observed to what we would expect if the factors were independent, so if there was no relationship. Now we can logically come up with our expected values on the basis of what we're trying to achieve, but that actually translates into quite a nice little formula, and to work out any expected value all we need to do is say, well, let's look at the row total multiplied by the column total and then divide by the overall total. So for example, if I wanted to get the corresponding expected for my first observed value of 25, well, I can see my row total is 118, and then I've got my column total of 143. Multiply those two together and divide by the overall total of 509. Now that's how we come up with 33.15. So I'm basically saying I've observed 25, but I was expecting 33.15. So a little bit of number crunching to do on the calculator for this tute question, but if we go through and systematically apply that formula, we can come up with our table of expected values. So for every one of the observed values, we've got the corresponding expected value. From there, we can set up our formal notation for our hypothesis test and use the comparison of observed and expected values to calculate a test statistic. Okay, so a test for independence Remember, the null hypothesis is always that our two variables are independent, and then the alternative is that they're dependent. So independent is the same as saying there's no relationship between them. Dependent is the same as saying that there is a relationship between them. So we set those up and also just remind ourselves that it's an alpha 5% test. We've got to do that comparison of what we've observed and what we expected. Remember, the expected, in using that formula, we were working out what we expected if the null was true. And that's how we do any hypothesis test. Now, the test statistic is a matter of looking at the observed minus the expected. You square it so that that's always a positive value, and then you make it relative by dividing by the expected. You have to do that for every combination of observed and expected pair, and then you add them all up. So for example, the first component of our calculation would be to compare the 25 to the 33.15. So you do that subtraction, square it, divide by the expected of 33.15. Then the next comparison, 22 to 26.69. So you do the subtraction, square it, divide by the expected. You do that for every observed and expected combination, and then you can add them all up. So this is a fairly computationally intensive question to work through, but it's good practice just to, get you into looking at each component. Probably write down each one to a couple of decimal places, and then you can add them all back up again. If we do that, we end up with a test statistic of 22.65. So remember, the whole idea of this test is that if there is only a small difference between what we've observed and what we expected, well, that's suggesting that the observed data does come from a situation where the variables are independent and it's just natural sampling variation. But if there's a big difference between what we've observed and what we expected if the null was true, well, then that's suggesting that we reject the null. So 22.65, is that a small difference or a big difference? Well, to work that out, we have to, of course, look at our decision diagram. Now, a test for independence is a chi-squared distribution. The test for independence, remember, is one of our special hypothesis tests. We're not looking at parameters as such, it's more the concept of independence. And given the test logic in comparing observed and expected, it's always an upper tail reject region for this test, because the only way we're going to reject the null is if there is a big difference between what we've observed and what we expected if the null was true. So an upper tail reject region, the area is 5%. We've got to get the cutoff. To do that, we have to look at our degrees of freedom. Now remember, it's rows minus 1 times columns minus 1. We've got 5 rows, 3 columns. That gives us 8 degrees of freedom. Now if you look up the 8 degrees of freedom row in your chi-squared table and look up an upper tail area of 5%, so that tells you what column, row 8, column for an upper tail of 5%, the cutoff is 15.507. So if we compare our test statistic to the decision diagram, the test statistic of 22.65 is clearly in that upper tail reject region. So our decision, written firstly in terms of the null, is just to reject the null. We can then put it in terms of the alternative. So if we're rejecting the null, we're saying there is sufficient evidence to conclude that there is a relationship between the managed fund type and level of return. And part B just wanted us to put it into a little bit more of a practical context. So what the decision is telling us is that, well, managed funds may spread the risk, but this does not mean that there is no risk. We're seeing that the level of return does depend upon the particular managed fund type. So it's not just invest in a managed fund and you'll do really well. There are differences depending on the type of managed fund.